Okay, YouTube, this is my last little video on my first module on lines and their graphs, in which we're going to discuss actually what we refer to as the general form of the equation of a line. And so up until now, we've talked about point slope form, this y minus y1 equals m times x minus x1. We've also included slope intercept form. What I want to kind of discuss is this, that sometimes, like x equals 5 would be the equation of some vertical line, but it can't itself be written in slope intercept form and backwards, into point slope form. So because of its slope being undefined, basically, that's the reason why we can't do it. But we can say this: there is one way to write the equation of every single line, and that would be expressed in the form ax plus by plus c equals 0, which we refer to as the general form of a line here. Okay, so we say every line has an equation that can be written in general form, every single one. And what I want to kind of indicate here is this: it's just getting all of your variables and constant term c on one side and then nothing left on the other side, or a 0 left on the other side. So we say a, b, and c are real numbers, and we'll accept the fact that because we want this to be a line, then we need x and y to exist, and that a and b cannot be 0 themselves. But this is what we refer to as the general form of the equation of a line. So what I would like to do is kind of play around with this form in terms of rewriting it so that we have, slope-intercept form, or possibly graphing out of general form without switching it into slope-intercept form first. So taking a look at checkpoint 7 here, it says find the slope and the y-intercept of the line whose equation is given in general form as 3x plus 6y minus 12 is 0, and then use the y-intercept and slope to graph the equation. So what I'm going to do is I'm going to say, well, if you get a line that comes in this package right here, and actually this is a difference there, okay, and we want to find what the slope and y-intercept are, the best way to do this, if it's convenient to do it, is to isolate the y value here. So what I'm going to do is I'm actually going to add the 12 constant to the other side and subtract 3 x's from each side here. So we'll take away 3 x's and add 12 to the right also. And so these will cancel on the left, and what we're left with is this negative 6y value equaling negative 3x plus 12. So our final step will be to divide everything by this negative 6 here. And because this is a monomial divisor, basically a one-term divisor, we can take everything on the right divided by this negative 6. So a negative 3 divided by a negative 6. And that would give us a positive 1/2. And I'm going to suggest we put the x off on the side. And then a positive 12 divided by a positive 6 is negative 2. So recall that the things we were after here were the slope and the y-intercept. And I can easily see now that our slope is a positive 1/2. We have a rising graph from left to right. And that our y-intercept is negative 2. And then in terms of sketching this, remember that we always start by sketching the y-intercept first. So I'm going to go down to negative 5 here, and I'm going to say, well, the negative 2 must lie right here. And because our slope is a 1/2, we're going to go up 1, right 2. I'll actually go out 5 on my x-axis here as well. We would go up 1 from here and right 2. And actually, I'm going to pull this stunt twice. I'm going to say up 1, right 2 again. And then I'm just going to play connect the dots here on our line. So this would be the graph of this equation over here, and we should certainly label it y equals 1/2 x minus 2. So that's how we could easily determine the slope and y-intercept of this general form equation, is just to put it in the slope-intercept form. Now I have to tell you that there are times in which graphing out of general form is actually a really convenient thing to do. And one way that we do this without putting it into slope-intercept form is by using intercepts, okay? So what I'd like to do is indicate here that when we use intercepts, what we're really doing is finding where our line hits the x-axis and where it hits the y-axis, and then playing connect the dots with it. But the reason why it's convenient here is because, well, let's consider these steps. We say to find the x-intercept, what we do is we allow the y value to equal 0 and then solve for x. In other words, when you have a graph with intercepts here, I'm just going to make an arbitrary linear graph here. I could say that this point right here is the point 0, comma b. And I'm going to refer to this point right here, which is our x-intercept, as just a, comma 0. I'm going to use a out of convenience since we use b here. But we can see that when we find an x-intercept, what we're really doing is we're allowing the y value to be 0 and then working backwards to solve for what that a value is. Whereas likewise, when we solve for a y-intercept, you actually set x equal to 0 and you solve for that y-intercept b. So again, to find the x-intercept, we're going to let y equal 0 and solve for x, and then plot that point containing the x-intercept on the x-axis. So you'll notice that I've got some other general form equation of the line here. I can tell this because it's set equal to 0 and all of my substance is on the left. So what I'm going to do up here is I'm going to write x-intercept. And what we're going to do is we're going to search for the x-intercept here. But what I want to point out is that when you search for an x-intercept, what you're really doing is you're plugging in 0 for y. And anytime you plug in 0 for this y value here in general form, what that's going to do is it's basically going to cause this term to drop out. And what you're left with is 3x minus 6 equals 0. So we could easily tell that, we could drop the 6 on the right side and then divide by 3, and we're actually just going to get 2. So our x-intercept here is 2. I'm actually going to go put that on our graph. I'm going to say, I know this line hits the x-axis at 2. I'm going to label this as well, 2, 0. So now to find the y-intercept, I'm going to make a little subheading here, y-intercept. We're actually going to plug in 0 for x, but a little bit more quickly this time, because what I'm going to say is this, well, I know that this term will drop out right here. So I'm going to get left with negative 2y minus 6 equals 0 because the x term just drops out. So now adding 6 again to the right side, I get negative 2y is equal to a positive 6. Well, then y must be a negative 3, which means that it hits our y-axis at a value of negative 3 here. I'm going to label this one as well, 0, negative 3. So just like any other line that we've graphed up until this point, what we're going to do is we're just going to play a little connect the dots. And I do want to make sure we label this. This is the line 3x minus 2y minus 6 equals 0, all of its solutions here. So really quickly before we tune out of this, one thing I want to kind of re-mention over this last module is our equations of lines. We have 5 different forms, okay, I guess you could say. The point slope form was our y minus y1 equals m times x minus x1. And our slope intercept form is always our y equals mx plus b. So now our horizontal and vertical lines, you can kind of think about them as backwards. You know, when I get students that make a mistake on graphing horizontal lines, they say y equals a number. They want to go graph it vertically because they're used to the y-axis going north-south, okay? What I'll tell you is that if you think about it that way, then just do the opposite, okay? So if it's y equals a number and you want to draw north-south, actually draw east-west. And then when it's x equals a number, we have a vertical line, we'll draw north-south. And then last but not least, our general form of this equation, this line, we could actually just turn this back into slope-intercept form if it doesn't get too ugly, or we can graph this using intercepts. Cheers.